Okay, so did you correctly predict what was going to happen? Let's have a look at a couple of points in the motion of that ball as it was swinging around now and discuss how the frequency that you heard changed when the ball was at that position. First of all, in this shot, the ball is moving backwards, so it's moving away from the microphone in the middle of the lecture theatre. So the ball in this case is the source. So the equation to describe the observed frequency is given by v, the velocity of sound, divided by v plus vs in this case. The plus sign because the source is moving away from the observer. So in this case, we end up with a smaller frequency, and so you hear a deeper sound. Okay, in this next photo, this is when the ball is traveling out of the screen towards the microphone in the lecture theatre. So in this case, the source is again moving while the observer is stationary, but in this case, the frequency is given by the equation f dash is equal to v over v minus vs. So we're now dividing by a smaller number, and we end up with a larger frequency. So in this case, it's a more high-pitched sound. Okay, now that we've discussed that, let's look at the video one more time and then I'll pose a problem for you to try. Now we can also have wind, which is when the medium through which the waves are traveling actually moves. So in these cases, the best way to deal with this is to choose a frame of reference that moves with the wind. So we take the wind as our reference frame. So probably the easiest way to see this is to work through an example. So let's take this situation again, where we've got an observer traveling towards the source. The velocity of the observer is VO, the velocity of the source is Vs, and the velocity of the waves through the medium is V. And we've now got wind traveling in the same direction as the observer. So in this case, traveling to the right here. And what we need to do is write an expression for f dash, the frequency that this observer now hears. Okay, so we've sketched our situation. Now, if there was no wind, the frequency observed by the observer would be given by v plus the velocity of the observer over v minus the velocity of the source. But there is a wind, and to account for the wind, we're going to measure everything from the wind's reference frame. So hopefully you remember your relative velocities. The velocity of the observer relative to the wind is equal to the velocity of the observer minus the velocity of the wind. And so according to the wind, the observer's actually going a little bit slower than they would be otherwise. Now the velocity of the source relative to the observer is equal to the velocity of the source minus the velocity of the wind. But these are in opposite directions. So it'll be negative, negative, or plus the velocity of the wind. So the source looks like it's actually going faster according to the wind. Okay, so now we want to get the velocity that the observer actually measures. In the wind's reference frame, the speed of sound remains the same, so we've still got v, but we've now got the velocity of the observer relative to the wind. So that's plus VO minus VW over v minus, now this is the velocity of the source according to the wind, so this is Vs minus VW. And so we've now come up with an expression for the frequency measured with the wind. So always just consider the reference frame of the wind, which could be going in the same direction as the source, or it could be going in the same direction as the observer.